record. Hi, everyone. My name is Matthew Robinson with the University of Central Florida, and today I will be speaking about a novel metric to quantify holistic health used for diet studies that we've been working on. So my name is Matthew Robinson. This project was done in conjunction with Ruben at Actor Rover. We are both statisticians. And then there was a clinical study part of this, which was done with Sharon Wasserstrom, Dr. Sharon Wasserstrom, Dr. Jacqueline Nienhuis, Dr. Salmaya Narayanan, and med students Dakota McCoy and Nisha Sharma. This presentation is going to focus on this mathematical index for diet optimization and not going to say much about the study. The study is pretty standard, so I'm going to give you a brief intro to the study, and then it's going to focus on the mathematics. The mathematics are pretty simple and straightforward, but very fascinating for, I think, an audience of endocrinologists. So next slide. Okay, so agenda. First, I'm going to start with an overview of the clinical study. So this makes sense what I'm about to talk about, and the clinical biomarkers and covariates measured in the study. Then I'll talk about the mathematical definition underlying holisticness and mathematical properties of this, what I call a desirability index, and I'll demonstrate how to use it, and there'll be questions at the end. So overview of the study. This was a paired study. All participants were measured at the beginning, pre-intervention, and the end of the study, post-intervention. Changes in the participants' lab measurements indicated if the treatment had an effect. So the hypothesis was that plant-based dietary intake improves holistic health for diabetic patients. So all the patients were diabetic, type 1, type 2, or LATA. And we measured them before enrolling in the study. Most of them were eating what we called a standard American diet, and then after 8 weeks on a mostly plant-based diet. Then lab tests were performed: A1C, CRP, total cholesterol, HDL, LDL, triglycerides, non-HDL insulin, also AST, ALT, pre-weight, post-weight, a few other things, blood pressure. Changes were assessed using a standard t-test and our proposed index, which is what this presentation is going to be about. So quantifying holisticness. So the definition of holistic is it's an adjective used to characterize by comprehension of parts of something as intimately, I can't speak today, interconnected and explicable by only by reference to the whole. If a patient, so some questions before we get to the mathematics. If a patient has a very bad lab value, say the blood sugar is way off, but everything else is perfect, are they healthy, or are they even, how unhealthy are they? Another question is, what about a patient that has several borderline values, like borderline high blood pressure, borderline high cholesterol? How healthy would you say they are? And then also, is this patient with several borderline values healthier than the patient who has a really bad A1C, but everything else is perfect? Another question you might ask is, how would you quantify changes in holistic health if you put a patient on, say, a low carb diet and they eat tons of meat, so their A1C gets much better, but their cholesterol gets much worse? Are they any more holistically healthy? Because you went from one problem to a new problem. So you fix one problem and caused another problem. Okay, so let's start leading into some more technical questions. So some so how would, now that you know the definition of holistic, how would you mathematically define it? How would you objectively measure if a patient is more holistically healthy now? This is a question I'm going to propose an answer to, because it's a very hard question to answer, because it's a trade-off. You can fix one health dimension, say blood sugar, cause another problem, another health dimension, say cholesterol. So it's like, did the patient improve? I don't know. So So some properties that we were looking for is the patient can't be quantified as being holistically healthy if any of their health dimensions are very bad, like diabetic levels of A1C or incredibly bad high blood pressure or other things. So then another property is we wanted a penalty if you have multiple dimensions that are not healthy. So if you have several borderline values, if you have one borderline value, you can just take like blood pressure medicine and fix it. But if you have several of them, borderline blood pressure, borderline cholesterol, borderline prediabetes, blah, 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 you could end up taking 10 medications and forgetting the medications, and there's interactions, and it really spirals out of control. So we thought it was important to have a penalty if you start to get multiple unhealthy dimensions or borderline unhealthy dimensions. Then also we wanted it to respond to improvements or worsenings in a very predictable manner. So the method we came up with has this nice property that it responds to relative changes in a very predictable way, which you'll see in a moment. So here's an intro to the math. I promise this math isn't going to get that hard. So try to hang with me. There's only about 3 slides on math, and then we'll go back to not doing math. So there's 2 types of means. I work in the field of statistics, so I'm well aware of this, but endocrinologists, this audience probably doesn't do much statistic. Anyways, so there's the mean or the average, which I'm going to call the arithmetic mean to distinguish it, which is basically when you add numbers together, then divide by the number you added. So if you wanted to take the average of 4 and 6, you do 4 plus 6 is 10, divide by 2, it's 5. The average of 4 and 6 is 5. So everyone knows how to do that. There's also another type of mean that's based on multiplication called the geometric mean. And the geometric mean typically gives similar values to the arithmetic mean, but slightly different. It's answering a slightly different question. So the geometric mean answers the question of what number when multiplied by itself is equal to a product, whereas arithmetic mean answers the question of what number when added to itself equals that sum. So anyways, if we look at this rectangle, the one side length is 4, the other side length is 9. We do 4 times 9, that's 36. So we want to know what's the average side length, or more specifically, what's the average side length that'll give us an area of 36. We want to keep the area constant. So we do 4 times 9 is 36, and we take the square root of that. That gives us a side length of 6. So the average side length is 6. If we use the arithmetic mean, it would give us not the correct answer, because 4 plus 9 is 13, divided by 2 is 6.5. And if you take a 6.5 on one side length and 6.5 on the other for square, it would give you the wrong area. So we can see that there's sort of 2 ways to answer the mean question. And so sticking with the geometric mean, which is basically the 2 side lengths multiplied and then take the square root, it extends very easily into 3 or more dimensions. In 3 dimensions, it becomes a cube. So what's the average side length on a cube? And beyond that, it's a hypercube, but it's not that hard to imagine. So the geometric mean, it's the square root of a times b. This is different from the distance formula, which is the square root of a plus b. So don't confuse the 2. So anyways, it has this property that you're multiplying these values together. We're going to pretend a is a health dimension, say blood sugar, and b is another health dimension, say cholesterol. And we're going to transform or recode the dimension. So 0 means it's unhealthy, it's like in the diabetic range, and 1 means it's healthy, it's normal or ideal. And so if any health dimension's near 0, that means it's unhealthy. And multiplication has this property that any number near 0 times any other number is going to be a very small number. or anything times 0. So right away, it has this property that you can't hide an unhealthy dimension. So if your A1C is way off, very low, it'll be near 0, and then in the multiplication, it'll drag the whole index down, the holistic health. So you can't hide an unhealthy dimension. Then you can look at the math and compare it to the arithmetic mean, where you can average out an unhealthy dimension. And this becomes particularly apparent when you have a bunch of health dimensions, 8 or 10. In this study, we had 10 health dimensions. And if you have one that's 0, but everything else is high, you can easily average out a health dimension. And I'll say the health is really good when it's really bad. So another property is there's a penalty for multiple unhealthy dimensions. So say you have 3 health dimensions: A is A1C, B is blood pressure, C is cholesterol. So if you have 2 bad ones, say A1C and blood pressure are low, when you take 2 small numbers multiplied together, it's an even smaller number. So 0.1 times 0.2 is 0.02, which I should have wrote on the slide, but I didn't. But anyways, long story short, it gives a penalty for multiple unhealthy dimensions because 2 small numbers multiplied together is an even smaller number. And you don't get that effect with the arithmetic mean. You still can get an averaging out effect, particularly when you have a bunch of health dimensions. Then the relative change. This is an interesting property, and the math isn't too hard, but I don't have a lot of time to speak about this. But long story short, if you do a 10% increase in any health dimension from any starting point, it causes the same change, same improvement in this index. And that's not true for the arithmetic mean, because a 10% improvement starting at, say, a low value isn't as big of a deal as a 10% improvement starting at a high value because of how the math works out. So this is very favorable because it makes detecting percent improvements very predictable, and it's a very nice property because it weights everything equally. It weights each health dimension equally, basically. So here's a sort of, I'll show you the index and then we'll talk some more about it. So the index is pretty simple. It's basically just the root of all the health dimensions multiplied together. And because it's multiplicative, it has all these properties that if any of the health dimensions are very unhealthy, meaning near 0, the multiplication will, anything near 0 multiplied by anything, no matter how big it is, will still be near 0. So you can't hide an unhealthy dimension. Then there's a penalty. I use the word harsh. I'd say moderately harsh penalty for multiple unhealthy values. So if you start having multiple problems, blood sugar problems, blood pressure, cholesterol, whatever, then you start to get this compounding effect, which is very favorable, in my opinion, for this type of study. And then it has this nice property that responds to relative changes in any dimension equally and regardless of the starting point for that dimension. And that's not true of the arithmetic mean at all. So it's a very nice property. And when the index improves, say 10%, that means one of the health dimensions improved 10% from where it was at before. So it's very nice. Okay, so now let's get into some data formatting. So this is very important. So the problem with this health data is some numbers you want higher is better, others lower is better, some you need to be near a target. So like A1C, the lower it is, the better, but HDL, the closer it is to whatever the target is for your sex, say 60, is better. So if you're above that, it's unhealthy, and if you're below that, it's unhealthy. So it's the distance from the optimal. And some things, the higher, the better, like O2 saturation. Or so anyways, so we need to recode everything so they're on the same scale, and everything, the higher it is, the better, because that'll make the mathematical optimization much easier. So we recode everything, which I'll talk about on the next slide, but basically, so 0 is unhealthy, 1 is ideal or perfect health, and 0.5 somewhere in between. And so all these variables are now recoded, so the higher is the better and on the same scale. And Now this makes optimizing it and comparing how holistic health improves much easier, because the geometric mean calculation, which is all these dimensions multiplied together, if the higher is better for each dimension, then when you multiply them together, the higher it is, the more holistically well balanced and healthy you are. And so, yeah. So A1C or desirability graphs. So the word desirability actually came out of industry, like trying to optimize the flavor of like Coca-Cola or whatever, what was most desirable to the people in the study. But anyways, I'm gonna stick with their wording. So for A1C, the lower it is, the better. So if we look at this graph, lower values of A1C, so the left side of the graph, they're higher on the y-axis of desirability, they're more desirable. And then higher values of A and C are less desirable, so they're lower. So for A1C, the lower is the better, so it goes from sort of the high at the top left and low at the bottom right. So we basically make a graph that has those shape properties. And then for this project, I set an A1C of 5.7 or whatever was the clinical guideline for pre-diabetes at desirability value of 0.5. I'll talk about that more in a second, but basically to read the graph, you go to the patient's lab value for A1C, say it's 7 in this picture, and you go up to the graph, 7's well above the pre-diabetes limit, and then you see where it is, and then you go across to desirability, and in this case, it's 0.35. So it's definitely not ideal, because if it was ideal, it would be near 1. So it's closer to 0, meaning unhealthy, than is to 1, meaning healthy. So we make these graphs for each health dimension. For this study, I based them on clinical guidelines, and I set the desirability of 0.5 where the pre-level was, pre-high blood sugar, pre-high cholesterol, pre-whatever. So that's how I made them. These graphs in reality should be made based on some survival analysis or hazard rate data, which I don't have, but I'm sure someone has. And yeah, so set the graphs, a little bit subjective. And then there's 2 ways to think about these graphs depending on the population. One is if the population starting from a very healthy state, then I would set the low desirability limits at the pre-level. But if the patients are starting from a very unhealthy state, then I basically make the graphs drag out a lot longer into the unhealthy range, so we can detect relative improvements. Also, these are very amenable, and you can change them based on the particulars of your study and your patient population and the demographics and ages and stuff and sexes, because it changes a lot of these values. So let's work an example. How am I doing on time? Running low on time. So basically, pre-diet, the patient's A1C in this example is low, their CRP, TC, et cetera, is high, HDL, meh. And then post-diet, it was whatever. So then we do the calculation, and pre-diet, their holistic health was 0.53, and post-diet, it was 0.8. So it says they had in this estimate, this case, a 27% improvement in holistic healthness. So they had a big improvement, particularly in A1C and also in HDL. So comparison to the mean. The mean has this flaw that you can basically average out unhealthy dimensions. And this actually occurred several times in this study. And so here's some mock data, but basically this person's A1C got really bad, but the other stuff was kind of meh. But anyways, a geometric mean will detect that the person's health got much worse holistically, but the arithmetic mean will say they got better. So that's very incongruent. And my professional opinion and the people I was working with from the study opinion was that the geometric mean better captured the patient's health status. So any questions? Thank you. Bye.